Hi, welcome to AP Calculus for East Aurora High School. Today we're going to be looking at approximating areas under curves using the trapezoid rule. So previously we've been using rectangles to approximate areas under curves. Now we're going to try to make it a little bit more exact by using trapezoids rather than rectangles. Today we're going to look at using equal intervals. So just like we did when we had rectangles, we want to take our interval from A to B and divide it up into n equal intervals. So the width of each interval is going to be equal to b minus a divided by n. Now if you take a look at the diagram here, you'll see that I have a trapezoid pictured the way we normally see a trapezoid, with the top and the bottom base parallel to each other. We're going to calculate the area of just that trapezoid, turn it on its side to fit it underneath the curve, and then add up the trapezoids underneath this curve. So, for example, let's say that I have the width of each interval is going to be this direction right here. So I'm going to call that the W direction. My bases, base 1 and base 2, are the two sides that are parallel to each other. So remember that when we take the area of a trapezoid, we're going to say that the area is equal to 1/2 the sum of the bases. Another way of looking at it is by taking the average of the length of the bases and then multiplying it by the other direction. In this case, I've called the other direction W. We could also call it h for height of the trapezoid. So if we go ahead and turn that trapezoid on its end, we'll see that we end up with this trapezoid right here underneath the curve, where I've got the first height as b1, the second height is b2. Those are merely the function values at each of my x coordinates at the ends of the intervals. And then the w value is how far apart the intervals are going to be. Let's go ahead and draw in another trapezoid. So I'm going to make my trapezoid this time going from 3 to 5. We'll go ahead and follow it up to the curve on each side and then connect those endpoints right there, making a trapezoid. You'll notice that, once again, we are using this side right here, which has a length of b2. And we're going to call the other side b3. The width of this interval is still w, so it'll look like this. Let's draw in another trapezoid. So this time I'll go right along here. And again, I'm focusing today on making my trapezoids have the same width. The intervals are remaining the same. So here I have my W. I am again using the value B3 for the left side of this trapezoid, and I'll fill in B4 to stand for this side right here. Let's make one more trapezoid here, and this next trapezoid will look like this. We'll make the heights as the heights on each end of the interval, connect those values. This first height is going to be B4 used over again, and the second height will be called B5. And again, we once again have our width of W right there. So what we'd like to do is then add together these trapezoids. So that tells me that the area is going to be approximately equal to, we want to go ahead and add together trapezoid number 1 plus trapezoid number 2 plus trapezoid 3 plus trapezoid 4. So you'll notice that I've replaced the area of trapezoid 1, 2, 3, and 4 by the formula for the trapezoids, filling in the correct base numbers that I'm using for trapezoid 1, 2, 3, and 4. Now, what you may notice is that we have a replication here. We see that base 2 is used here, but it's also used here. Base 3 is used here, and again here. Base 4 is used here, and again here. Again, remember that those bases really stand for our function values. So I'm going to write then as my trapezoid rule that the area is equal to, I'm going to pull the 1/2 W out in front of the whole thing. And then you'll notice that because I've got base 1, that's the function value at x1. But then base 2 would be the function value at x2, but I'm using that one twice. So I want 2 f of x2. I'm using b3 twice, so I'm going to say 2 function value at x3. And so on until I get to, let's see here, 2 function value at x4. And the last one, the function value at x5, is only used once because it was only a side on the last trapezoid. So this is how I can represent the sum of my trapezoids by combining like terms. So go ahead and pause the video. Make sure that you write down in your notes both the diagram, the area formula, and then how that transfers over to the trapezoid rule that we're going to be using, so that we can go on and try some specific examples using functions. So go ahead and write this example down in your notes. Again, you may need to pause the video so that you have enough time to write down the example and to draw a diagram. We're going to use the trapezoid method to find an approximation for the area underneath the curve y equals x squared minus 2x plus 3. We would like to use the interval from 0 to 3 with an n value of 6. So of course the first thing that we're going to do is calculate the width of each interval because we want them all to be equal. So we're going to say b minus a divided by n. So 3 minus 0 divided by 6 tells me that the width of each interval is 1/2 or 0.5. So once I find that, I'm going to go ahead and set up a table of values beginning at x equals 0 and continuing to x equals 3, counting by 0.5s. So make a table of values, enter this function into your graphing calculator, and please fill in the table of values with the correct function values. Pause the video and then come back and check with mine and make sure that we agree. So I've completed my table of values and gotten function values at each x value from 0 to 3, counting by 0.5s. Now let's take some time and draw in the trapezoids. Remember that we want 6 trapezoids. We're going to start at 0, and the width of each interval is equal to 1/2. So my first trapezoid would go from 0 to 0.5. I follow the height up to the function on each end of the interval, and then I connect those function values. Go ahead and make the second one from 0.5 to 1 and connect those endpoints. The next one will go from 1 to 1.5. There are my endpoints and connect. Then I've got one going from 1.5 to 2, going up to the curve at each endpoint of the interval and connecting those endpoints. From 2 to 2.5 will be my next one. Connect the endpoints. Notice that really what I'm doing is making secant lines to connect those endpoints. So connecting my last two from 2.5 to 3, I see that I have 6 trapezoids. Now I'm going to go ahead, because I have equal intervals, I'm going to use the trapezoid rule that we had on the previous page. So that trapezoid rule says to approximate the area under the curve, we're going to take half of the W. So we've got to say half of W, which is also 1/2. So I'm taking half of half. Now I want the first function value, so I want f of 0 to come first. Then each in between one is being used twice, so I want 2 times f of 0.5 plus 2 times f of 1 plus 2 times f of 1.5 plus 2 times f of 2 plus 2 times f of 2.5, and then we'll finish it off with f of 3. So you'll notice for this trapezoid rule that only the first and the last sides are used once. All the rest of those heights are being used twice, once in two different trapezoids. Now I really need the function values here, so I'm going to say the area is equal to 1/2 of 1/2 is 1/4, and then we will fill in our function values. So the function value at 0 is 3. We'll multiply the next one by 2, so 2 times 2.25 is 4.5. 2 times 2 is 4. 2 times 2.25 is 4.5 as well. 2 times 3 is 6. 2 times 4.25 is 8.5. And then the last function value only gets used once, so then I'll add on the 6. Now when I add all of this together using my calculator, I ended up with a total of 9.125. Now that area is actually a very good approximation for the area under the curve. I can tell that I haven't left off very much area and I haven't counted any extra. So when we learn later on in this chapter how to actually use calculus to find the area under the curve, we'll see that the actual area is pretty close to 9.125. And that was just using 6 subintervals. So you'll notice that as we add more intervals, we'll get an even more exact approximation. But this is quite a good approximation for the area under the curve. In our next example, I want to introduce some new notation that's going to represent find the area under the curve. So you'll see that this is the notation that we're actually going to see in our textbook as well. This notation means the function is 4 minus x squared. So I've given you the graph of the function f of x equals 4 minus x squared. This notation means find the area underneath the function 4 minus x squared. This symbol is going to mean to us take the antiderivative, but the antiderivative actually means find the area under the curve. These endpoints tell us where to begin and end our interval. So this is telling me start at 0, go to the number 2, and I'm going to then have to tell you how many trapezoids to use. So in this example, what we are saying is our interval goes from 0 to 2 with an n value of 4. So when I calculate my w, I'm still going to say 2 minus 0 divided by 4, which again for this example we're going to use 1/2 as our width. So go ahead and make a table of values. For our table of values, we want to start with an x value of 0. And we want to count by 1/2, or 0.5, so we want to say 0, 0.5, 1, 1.5, and 2. Go ahead and plug this into your graphing calculator and get the y values and come back and check with mine. So check your y values with mine, and now let's take a few minutes to make our trapezoids. So my first trapezoid will go from 0 to 0.5. Go ahead and make those heights and connect the endpoints. Next interval from 0.5 to 1, make the heights, connect the endpoints. Next one goes from 1 to 1.5, make those heights, connect the endpoints. The last one actually turns out not to be a trapezoid, but instead to be a triangle, but we're going to calculate it in exactly the same way. So going ahead and setting up our area, we're going to say that the area is approximately equal to 1/2 of the width, so 1/2 of 1/2, times the function value at 0, plus 2 times the function value at 0.5, plus 2 times the function value at 1, plus 2 times the function value at 1.5, plus the function value at 2. And when I fill in these values and get an approximation for my area, I'm getting 1/4 times the number 4 plus 2 times 3.75, which is 7.5, plus 2 times 3, which is 6, plus 2 times 1.75, which is 3.5, plus my last number, 0. Now take a minute, go ahead, plug those into your calculator and see if you can get the area and come back and check with my answer. I got as my solution 5.25, and again that's a very accurate answer for the area underneath the curve, f of x equals 4 minus x squared, going from 0 to 2. We used 4 trapezoids in this example. If we increase the number of trapezoids, we would also increase the level of preciseness of our approximation. For our last example tonight, let's take a look at a trig example. So I've got the function y equals sine of x, and I've graphed it from 0 to pi. I'd like to use 4 trapezoids. So, figuring out the width of my interval, I'm going to say that w is equal to b minus a divided by n. So, b minus a divided by n in this case is going to be pi minus 0 divided by 4, or pi over 4. Now, I'm going to have to be very precise and not round that to a decimal. I'm going to use pi over 4 in my calculator. So, first of all, notice that on my diagram, I'm going from 0 to pi. So halfway, this decimal right here actually represents pi over 2. This decimal represents pi over 4, and this decimal would represent 3 pi over 4. The graphing program that I use to make these graphs won't let me put pi's in there. It just puts a decimal approximation. Now, if I want to find the area, I'm going to have to go ahead and find the answer for sine at each of those function values. So I know that I need 0, pi over 4, pi over 2, 3 pi over 4, and pi. I can clearly see that the first one and the last one are 0. I know that pi over 2 has an answer of 1. And at pi over 4, sine is radical 2 over 2, and that's also the case at 3 pi over 4, radical 2 over 2. So my area is going to be equal to 1/2 the width. Now this time the width is pi over 4, so I'm going to have to say 1/2 times pi over 4. Now I want my first function value, so my function value at 0. I want 2 times the function value at pi over 4. I want 2 times the function value at pi over 2. 2 times the function value at 3 pi over 4. And the function value at pi, just one of those. Let's go ahead and fill those numbers in. So half of pi over 4 gives me pi over 8. Function value at 0 is 0. I'm going to multiply my pi over 4 function value by 2, so that's going to give me a radical 2, plus 2 times 1 is 2, plus 2 times radical 2 over 2, which is also radical 2, and then my last function value is 0. Go ahead and type those into your calculator and get your approximation. I got as my approximation 1.896. You'll notice that I didn't take the time to go ahead and make those trapezoids, so you could go ahead and fill in 4 trapezoids between 0 and pi. The left trapezoid and the far right trapezoid actually both turn out to be triangles, though. So thank you for working tonight on the trapezoid rule. In class tomorrow, we'll be working on some more trapezoid rule examples. Be sure to bring your textbook to class tomorrow and make sure that you've taken notes on this video. Have a great night. We'll see you next time. Bye-bye.